Okay, Algebrainiacs, so we're moving ahead into higher degree equations. This will be assignment number 12. Before we do that, let's just do a little bit of a recap, all right? So why is this called a higher degree equation? Well, here's a recap. So just remember, when the variable is to the first power throughout the entire equation, that was linear. That was assignment number 8 that we covered prior to spring break. And then when the variable is to the second power, that's called quadratic. That was assignment number 11, and that was also covered before spring break. Now we're ready for assignment number 12, higher degree equations. And this is a higher degree equation because you'll notice that that exponent there is a 4. So any power higher than 2, we're going to put into the category of a higher degree equation. This would be example number 1 in the notes that were sent to you. So just keep that in mind. If you would get those notes out and have them ready before you start watching these videos, that would help a great deal. So anyway, you notice that that power is 4. Any power higher than 2, for our purposes, we're going to consider that to be a higher degree equation. So again, in the notes that were given to you, I gave you my family recipe brought over on the boat from Sweden for a higher degree equation. So we go through the preliminary steps of simplifying. We talk about whether or not there's any fractions to clear. Clear fractions? We see if there's any distributing that needs to be performed. Distribute. And then, of course, everybody's favorite, combine like terms. Combine like terms. My Donald Duck is really out of practice. But anyway, none of those things apply to this first example. So we move forward. And just like we did on assignment number 11, quadratic equations, we then check to see if the variable happens to be in just one term. And if you notice here, that is the case because the x is in one term. All right, and you'll notice that this flow chart, if you will, has a lot of similarities to the quadratic one that we did prior to spring break. So that's good. Anyway, if you recall, and you have these already filled in, so you don't have to pause to write these things down, just take a look at it right there in front of you. But if the variable is just in one term, you might remember that we used inverse operations. We get x by itself, and basically the idea was inverse operations. The idea behind this, again, would be the order of operations, parentheses, exponents, multiply and divide, add and subtract. So as you recall, what we said was, when the variable's in just one term, let's get rid of all these operations that surround the x, and we always ask ourselves, which of these operations is furthest down the list from x? So if you go through the order of operations, parentheses, I don't see any parentheses, exponents, that would be the fourth power, multiply, that 2 is a multiplier, there's no dividing, add, there's no adding, subtract, all right? So notice that that subtraction is the furthest down the list from x. So we would get rid of that subtract 38 with what operation? How about add, Mr. Cinnamon Bread? Add, that's right, good idea. The opposite of subtracting is adding. So we'll add that 38 over to the other side. And again, these are inverse operations. We get rid of that addition with subtraction. Or we get rid of the subtraction with addition in this case. So then the equation transforms into 2x to the fourth power equals 38. And again, we just use the fact that adding and subtracting are inverse operations and therefore get rid of each other. Going back to square one, again the same thing. Parentheses, exponents, the 4 is an exponent, multiply, that would be the 2. So I hope you would agree that we now want to get rid of the multiplication by 2. And of course, the inverse operation of that is division. All right, again, when you guys transfer to Stanford next year, you will say inverse operations, all right? But here in Burlingame, Kansas, we say opposite, all right? Multiply and divide is opposites of each other. Okay, but anyway, so we use that idea that we get rid of multiplying with dividing. This would be the point in the process where I would suggest that we stop, because we're going to see 4 scenarios here that we'll go through, all right? Examples 1 through 4 will cover these 4 different scenarios as to the signs of the answers. So I want to ask you all to think a step ahead with me and think about whether the value of x could either be a positive or a negative number, all right? So let's think about this. If you were to plug a positive number in there for x and raise it to the fourth power, isn't a positive number to the fourth power positive? And I'll point out that that 19 over there is indeed a positive number. So I would suggest to you that x could indeed be a positive number, so we're going to keep that one. Again, there are 4 scenarios and they all behave in different ways. Negative. If we take a negative number and raise it to the 4th power, and the thing that we need to note here is that 4th power is an even power, all right? And that dictates a lot of the behavior as we move forward. But if you take a negative number to an even power, as we discussed on assignment 3, exponents, negative numbers to even powers come out positive. So yes, negative makes sense as well. So indeed, x could either be a positive or a negative number. Keep that in mind. That's going to change as we go through the 4 scenarios here. So now the question becomes, what math operation gets rid of a 4th power? And I would hope you would all agree that that would be a 4th root. So if we apply a 4th root to both sides of this equation, we'll take the 4th root of the x to the 4th, and we'll take the 4th root of 19. That'll get rid of the 4th power, all right? So this side transforms into just plain old x, because again, that 4th root gets rid of that 4th power, inverse operations. Now, here's where it can be a little tricky as to the calculators that we have out there in the world. Many of them have a dedicated square root key. However, it's more of a challenge when you get other roots like 4th root. So instead of saying, hey, Mr. Sonogram, would you come over to my house and help me find my 4th root key? I can't do that, I'm afraid. But I have discovered over time that a wise way to do this is to, instead of looking for the 4th root key on all the calculators out there in the world, let's change this into an exponent. So I want to remind you, as we talked about on assignment 7, radicals, that 19, since it has a first power implied, that this could be changed into a fractional exponent as 19 to the 1/4 power. All right, and that is a little more universal in my experience as far as getting that into the calculator. Now, when we do so, and I'm about to do that here, and you won't be able to see it, but you always want to make sure when you take a base like 19 and raise it to a power, that you put that 19 in parentheses. So I'm putting parentheses 19, close parentheses, raised to the power of. We talked about that on assignment 1. And then make sure you put this 1/4 power in parentheses as well. So 19 in parentheses raised to the 1/4 power in parentheses. And then this is where we would need to make sure that we pay attention to how far we're supposed to round it. This one says round all solutions to 2 decimal places. So I'm looking at the thing that, yeah, you can see it, can't you? But I'm looking at that number, and if you were to round it to 2 decimal places, I'm seeing 2.09, and it needs to be noted the calculator only tells us the positive root. But given the discussion we had earlier, the negative would also work. So we're going to put positive 2.09, comma negative 2.09. And those two would be our real solutions to this equation. Now there's others out there, but this was asking us just to find the real solutions. So that'll suffice. Now, I'm going to go ahead and set the stage for a discussion about the different scenarios. And again, we just got rid of that 4th power with a 4th root. Those are inverse operations. It's now time to begin the discussion of reviewing the behavior of different roots. All right, so if you would flip to the page that was sent to you that says behavior of roots at the top, and let's just go through these 4 scenarios. And example number 1 will illustrate the first scenario, and then we'll fill these in as we do examples 2, 3, and 4. So, this was an even root. 4th root is an even root. Just like a square root, 6th root, 8th root, 10th root, even roots, all right? And if we apply an even root on top of a positive number, and by the way, the 19, the thing under the radical, is called radicand, all right? All together now, radicand. So if we apply an even root to a positive number on top of a positive number, we will get 2 real solutions, positive as well as negative. Positive or negative 2.09. So that's scenario number 1 when we talk about the behavior of roots. And we will illustrate the other types of roots as we move forward. So anyway, Speaking of the Roots, why don't we listen to a little bit of music by the Roots as we fade out here? You'll notice they haven't fixed my speakers. They still are bad. Oh well.